Okay, this little video looks at specifics relating to the types of graphs you might find in Unit 3 Area of Study 2 and how you should attempt them and what little details to make sure you're paying attention to. So, first of all, rate of reaction graphs. Now, normally your x is the amount of time, your y is the amount of product, which means that the slope of the graph is showing the rate. So that blue one is at a steeper slope, so it's at a faster rate. Where it levels off, that's showing one of two things. Either that equilibrium's been reached, or that the reaction's gone to completion. Now, as you know, some reactions go to completion, some don't. So, if you get, say, a higher temperature, you've got to show two things. Firstly, yes, a faster slope at the beginning, showing that it's starting off at a faster rate. But secondly, it has to level off first. Okay, whichever one is at a faster rate has to get to the leveling off point first, and it has to have that steeper slope. If you're making the same total amount of product, then they're going to level off at the same point. Sometimes you'll be getting a different amount of product, which means you've also got to think carefully about where they level off. Okay? Now you're mostly going to see a substantial change like that in a rates question, where you're using a different concentration but the same volume of your limiting reagent. Okay? So like the difference here between the blue line for 0.8 molar and the orange line for 0.4 molar. Okay? 0.8 molar, you should notice three things. Firstly, starts off at a faster rate, so that's steeper slope at the low times. Secondly, it's leveling off first, because it's got a faster rate of reaction, so it's getting to equilibrium or getting to the point where it's reached completion first. And then thirdly, of course, it levels off higher, because you've got a greater amount of your limiting reagent, so you get a greater amount of your product. You're not normally going to have to worry about this and worry about Le Chatelier's at the same time, though. Okay, you're normally worrying about one or the other. Do not overthink things, do not overcomplicate it. Equilibrium graphs. Now, reaching equilibrium, if it's a rate time graph, then they've got to end up at the same rate. And this is the same if we're changing the position of equilibrium and then we're looking at what happens to the rate. Okay, when they get back to equilibrium, the rates have got to be the same. Okay, if it's a change, then you look to see, well, which one increased by the most, because that tells you which way it's going. So when you made the change, the stress, like an increase in temperature, or adding some product, or adding some reactant, something like that, whichever rate increases the most, that's the direction that it's going in to reach the new equilibrium. So if your forward one increases most, you know you're going to have a net forward reaction. If it's an amount or a concentration versus time graph, then the amounts at equilibrium have to be steady, so we get no change in amounts, but they don't have to be equal to each other. When we look at the change, the amount from where they started to where they end up at equilibrium, that has to be dependent on their molar ratio. So in this example, the reactant line goes down basically by the same amount that the product line goes up. That would indicate a 1-to-1 ratio. If it was 1-to-2, then the product line would have to go up twice as much as the reactant line goes down. Okay? And when we say about, when you are plotting graphs like this, you need to be measuring. Okay? Hopefully you'd have grid lines, so you'd be counting squares and measuring that way. Now, in a Le Chatelier's graph, we look at the changes that occur. And there's a couple of key things to look out for. Firstly, if you look between 0 and 4 minutes, that's clearly at equilibrium. There's no change occurring. At the 4 minutes there, line mark there, you see the lines start curving. There's no straight line up and down at any point. That is definitely a temperature change. Whether it's gone up or down, well, then you have to look at your system. Okay, so in this case we favoured a net forward reaction. It's an endothermic reaction, so it must have been a temperature increase. It gets back to equilibrium at about 8 minutes, and then at 10 minutes, now look at the CO line. That's got a straight line down. Anytime you see a straight line up or down for just one substance, that tells you definitively that you have added or removed that substance. Okay? So we've removed some CO, and then notice that we get partial opposition. So the concentration goes down from about 0.85 down to about 0.05, and then it rebounds slightly, but definitely not the whole way. Okay, that bit there, where it's got the rebound, the curve, that is exactly mirrored by the Cl2, because these ones are in a 1-to-1 ratio. So the change, the curvy bit, that has to be exactly the same for both of them. And the COCl2, that's a mirror image, because it changes by the same amount, but in the opposite direction. Note that they all get back to equilibrium at the same time at around about 12 minutes. Yep, so, and those are dead straight lines going exactly horizontal. They're not wibble wobbling. Okay, you need to be using a ruler. Okay, and then time 14 minutes. Notice all the lines go straight down. Okay, now all the lines going straight down, that tells you one of two things has happened. If it's aqueous things, then it's a dilution. If it's gaseous, which this one is, then it's a volume change. And of course the concentrations went down, which means the volumes went up. And then we get a partial compensation. So the ones that go back up, they go back up, but not to where they were before. Okay, unless you're given data, you don't have to know exactly how much they go back up by. Just make sure it doesn't get back up to where they were before. Now our molar ratios, the one before, they were all 1-to-1-to-1. So the change had to be the same. Here, we've got a slightly different one. We've got a 1-to-3-to-2 ratio, and that must be shown in the curvy bits of the line. So our N2 is just got the 1. So that will curve the least. The NH3 has to curve in the opposite direction because it's on the opposite side of the arrow, but it has to change its concentration by twice as much as the N2, because each time you use one N2, you make 2 of the NH3s. And the H2 has to change, has to go down by 3 times as much as the N2 goes down, because, of course, each time you use one N2, you use 3 of the H2s. Now, again, you have to plot this. This has to be accurate. You need your ruler out, not just to draw nice straight lines when they're back at equilibrium, but also to measure these distances. Or if you've got grid lines, you count the squares. So the last thing to think about is some concentration ratios. So we're back to this graph. And I want you to look again at the time 14 minutes. You notice there all those lines go straight down, but they don't always go straight down by the same amount. That's important because our volume has been increased. But because concentration is amount over volume, the new concentration is going to depend not just on how much you've increased the volume by, but what those initial concentrations were. So in this instance, what we've really done is we've taken the whole thing. It had a volume of 2 litres. We've increased it to 3 litres. So the concentration of all of them has gone down by 1/3. Okay. For the Cl2, that starts with a concentration of 0.12. When it goes down by 1/3, it ends up as 0.08. So its change has been 0.04. Whereas the CO, same ratio, still gone down by 1/3, but it's only gone down by 0.02. And the COCl2 has only gone down by 0.01. Okay, this is a mathematical rather than a chemical thing that's going on here, but it's still important that you represent it accurately. So whichever line starts highest up has to have the biggest change. Okay. If you see something like this, it's most likely to be with easy numbers, so it's most likely to be that all the concentrations would be halved. So then you've just got to show that with the correct ratio on there. Now, electroplating, you may also see some graphs, okay? Or you may have to draw graphs even. In electroplating, the most common thing to see is the relationship between the charge and the mass of metal that's deposited. Now that is dependent on two things. It's dependent on the charge of the metal ion, and it's also dependent on the molar mass of the metal. So if you look at silver and lead, for instance, now silver we know has a 1+ charge, lead has a 2+ charge, but per coulomb we're depositing pretty much exactly the same amount. Okay? That's because whilst the molar mass of silver is 107.9, the molar mass of lead is 207.2, so it's almost twice as much. Okay, so 1 Faraday, which remember is 1 mole of electron, which is a charge of 96,500, will give you 1 mole of silver and a mass of 107.9, but it would give you only half a mole of lead. But half a mole of lead has almost exactly the same mass. It's got 207.2 divided by 2, so it's going to give you 103.6. Yeah? So if you are thinking about that relationship, you have to look at both. You have to look at the charge on the ion and the molar mass of that metal.